Hello, everybody. My name is Abby Smith. I am currently a senior in biomedical engineering at BU. Thank you guys so much for coming to see my presentation. I have some family here, friends, and my Kilachand professor, so that's really awesome. But like I said, I'm an engineer, so my senior design project for this year was to develop a soft robotic tool for safer blood clot removal. And hopefully this is a good transition from the last presentation, that hopefully this will be a good use of robotics and AI instead of the destructive use of it. So my inspiration for developing this project was that my best friend's dad had a stroke as a result of embolism from a blood clot breaking apart. And I worked on this with my senior design team, as well as my advisor, Professor Sebesta, who is the director of the Robotics Center on campus. Oh, well, I guess my animations didn't convert on this, but that's okay. So what is a blood clot and why are they dangerous? A blood clot is when your red blood cells coagulate together in your veins or arteries. And the problem with that is that your blood can no longer pass to deliver oxygen to the critical organs in your body. Another problem is embolism, which is when the blood clot actually breaks apart into smaller pieces and travels downstream to further obstruct smaller blood vessels. So there's a picture there. And that's actually what causes things like stroke, which is when there's no oxygen that can get to your brain. So huge problem. So, like I said, this is a huge problem across the world, and in the US alone, there's over 900 cases of blood vessel or blood clot problems every year, resulting in over 100,000 deaths annually, which is a 1 in 9 fraction, which is very bad. Like I said, causes a lot of fatal health complications. And the big problem with this is in current surgical operations where they go in to try to remove the blood clot or treat it, there is a 42% chance of emboli incidence rate. So when they go in to fix this problem, there's a 42% chance they're going to make it worse, pretty much. And that can also cause like bleeding and other things. So going into the current solutions right now, the most popular is the mechanical or the stent approach, which is where they kind of put in this metal mesh and then pop it up in there. My dad actually has one of those. But the problem with that is it's metal, it's hard, and it's going to cause a lot of trauma to the vessel walls, lots of bleeding. And with these little fish, you can see that the emboli can still travel through there, so it's not very effective in limiting that. And on the right, there's the suction aspiration approach, which is pretty much like going in blind with a vacuum cleaner, and there's not a lot of ability for flexibility and moving around in there because this is a rigid metal rod. So obviously, we need something safer and more effective, which is where my project comes in. So we are aiming to fix vessel trauma using cameras, controls, which is actually air control, pneumatic control, so it's softer and more delicate, and also the use of soft materials like elastomers. You can think of those as something like silicone or rubber that's a lot softer versus the metal and hard tools that they're using now. And then we are going to aim to fix the problem of oxygen deprivation and embolism using a soft net with adjustable pore size. So this is a diagram of the tool that we have right now. So on the left, we have developed a stabilizer that is cable actuated. So when you pull on the cable, these soft pieces, they pop up and conform to the walls of the blood vessel. And that keeps the tool stable during the operation to allow for more precision. Then in the middle, you see the soft robotic aspirator, which is the most important part that I worked on developing. So this is essentially a soft vacuum that when you control it using air, it can bend, like curve like this, like in all different directions around the blood vessel to make it easier to remove the clots. And then lastly, there is a deployable net, and you can adjust the size of the holes on that, and that also pops up to keep emboli from traveling down the bloodstream while you're removing them. So yeah, just breaking that down again, we have an IR camera infrared, which detects clots using temperature, so you can have vision. Then we have the tool stabilizer, which pops up to hold the tool still. Then we have the vacuum aspirator to actually remove clots. And then to keep things from traveling downstream, we have a net which determines if the blood flows too high or too low, and if the camera sees embolism, and it adjusts the size of the holes to catch emboli but still let oxygen pass by. And then my approach to this pretty much was first by designing everything with a computer-aided design, kind of just based off of the functions that I wanted the different parts to do during the operation. Then I simulated everything to make sure that nothing was gonna explode when I pumped air into it. And I did lots of motion modeling and durability tests to make sure everything was gonna work out. Then I fabricated everything using either 3D prints or molding using silicone and curing them in like an oven pretty much. And then lastly, I did some verification of the motion to make sure it worked like I wanted it to. So I don't know where the rest of that title went, but so pretty much I did like a motion capture. So I had this device and with a fluorescent part on the part I wanted to track. And then I put known values of pressure into the chambers in the device, and then I used motion capture to map the motion. And then I was able to extrapolate that into 3D to show that this can actually bend in all directions and it works like it's supposed to. So yeah. In conclusion, this project will address critical limitations of current methods. It will reduce complications and improve patient outcomes, and it will advance the field of medical soft robotics.
We have about 4 minutes for questions.
Sorry, thank you.
Sorry about that. Really nice presentation, Abby. So my high school biology makes me remember that arteries come in different sizes.
Yes.
So what's the limit on this? And then, what's the prognosis? Or, if it's a really little one, then maybe it's not a problem because the body finds a way around?
Yeah, that is definitely true. So I forgot to mention the prototype that we made is more in like the inches scale. We made a scaled up one. Yeah, it's kind of like this big, yeah, length, and then diameter, it's probably like this big. Obviously, that could not fit inside of your arteries right now. That's just due to our limits of fabrication in the kind of general workshops at BU. But you're exactly right, where there's some major arteries, which is where we'd want to focus the most, because the smaller ones, you can kind of treat them easier using medication. And they're developing some sort of like tiny magnetic robots right now. But mine is more for the larger ones, which would probably be between the 10 millimeter diameter down to like 5 millimeter diameter, which is still pretty small. So that's what I'm gonna do, tackle that problem after I get my master's in robotics next year. Thanks.
Any other questions?
Yeah.
Maybe you can't answer this, but I was wondering, what is the process for having something like this be approved, like in comparison to like the drug process?
Yeah. So there's a long process to actually go through all of the regulations to get this actually into surgery. And we are a long way away from that. We just have our scaled up prototype kind of proof of concept. So right now what we're pursuing is the early patenting process. And then I'd like to come back to this problem when I feel more ready to tackle it in a fuller sense in making a more real prototype. But yeah, we'd basically have to go through like the whole patenting process and work with like through different regulatory processes to make sure there's like biocompatibility. I have to do assays with the materials to make sure this is going to work in the blood. And actually, you have to test it on, unfortunately, animals first to make sure that it works. And yeah, so I'll have more info on that next year.
If you ever